Good morning. All right, welcome to our last lecture here in MAC2311, Calc 1. So, pat yourselves on the back. You've made it all the way through. We're very near the end here. I feel like we've covered a meaningful amount of the U substitution practice. So I would be happy to do a mixture of things today. I don't have any fresh theorems or any totally new techniques to share with you, so we are in a review place, but exactly how we divide up that time, I think, is still important. So get the .cam fired up. A little bit later today, let's get some announcement-y things out of the way. Who's today, the 8th? Yeah. All right, so exam 3, which is the take-home, is going to be posted today. It'll look something like, here, let's dig into one of these old guys. Calc 1 in here. These are all Calc 2s. Anyway, oh, no, don't have them. So, whatever. So it'll look something. It'll look something like this. It'll be a PDF looking like this, and you'll print it up, write down your answers, and then scan those back in. And you'll have until Tuesday. Tuesday is also the day of the final. And you don't have to, normally when I do this, I have to, I usually make the take home be due at the final. But I'm comfortable with you handing it in anytime on Tuesday. There's a question, if we don't have a printer, is it okay to handwrite it? I would really prefer it be printed. I want to be able to turn the grades around quickly, and the organization is so important. So if you don't have a printer, I'll say this. If you don't have a printer, please be very neat. Meaning, like, try to follow the organizational scheme of the test itself. When it comes to the free response problems, especially, make sure that you clearly number the problem, write the problem out, and then your solution. If I just get a bunch of scans of like jumbled work, it's going to take me much longer to grade because I have to go through and sort out exactly where everything is. So if you don't have access to a printer, I'm not going to like refuse the test because it's not printed. That would be a horrific thing to do. But I would much prefer it be printed if at all possible. And if it's completely impossible, then yeah, of course, you can write it out by hand, but please be neat. So that is that. The final exam. And unfortunately, I can't be at all flexible with the final schedule. This is something that that Santa Fe takes pretty seriously. We have to stick to the schedule that they give us. So for us this term, I think yours is at 8. That's not it, is it? There it is. Okay. So yeah, from 8 to 10 a.m. So probably what I will do is I'll have the final open at like 7:30, and I'll have that window go from like 7:30 a.m. to 10:30 a.m. But please try to take it between 8 and 10. So the final exam is next Tuesday. From 8 a.m. to 10 a.m. I'm not allowed to be playing with this. It's a Santa Fe policy. For hybrid classes. If there is some sort of conflict there, you need to let me know immediately, and I'll have to clear any changes that we're going to make with my department chair. 8/11 is the day of the final, so I am 99.99999% sure that the 11th is Tuesday. Yeah, and then I can double check here in eStaff. So we can be certain. So this is us. And our final says here, exam, yeah, 8/11 from 8 to 10. So the final is definitely Tuesday, next Tuesday from 8 to 10 a.m. So please try to be prepared, try to be on time, because I really don't have a lot of room to be flexible there. If there is a conflict that's totally unavoidable, like nothing can be done about it from your end, then let me know immediately, and I will try to clear with my chair some alternate testing time. If you have any special arrangements through the DRC or anything like that, make sure that you file the test request with them, make sure everything is set up ahead of time. We don't want any issues. We want to make sure that you can use all of those 2 hours to actually work the final. A word on grades. So if you want to talk about grades, come to my office hour this afternoon. Normally in an in-person class, I can get a much better feel for how people are feeling about the material. I can watch your faces, you know, as I present things on the board, and we can have little conversations after class. And we don't have so much of that in these online hybrid classes. So it's possible that and I'm not saying this is the case for anybody, I'm just saying that this can happen, and I've seen it happen more in the online classes. It's possible that you get to this point in the semester without realizing that you're in kind of a difficult situation. I don't want this class to be ruinous to anybody's GPA. And there are things that we can do. If you're in a position where you cannot earn the grade you need in this class, we have essentially 2 options. One of them is a late withdrawal, and then the other one is an incomplete. And of course, the other option is to just like kick ass on the final and get a great grade. But I know that the reality of the situation varies quite a bit from person to person and situation to situation. And if you're feeling trapped right now, if you're feeling like, shit, it's past the withdrawal date, the final's coming up, I'm not in a place where I can do well, please come talk to me, and we can figure out which of those paths is the best path for you. Sometimes I can do a late withdrawal after the withdrawal period, sometimes I can't. It depends on a handful of things, you know, whether you're dual enrolled, whether you're using this or that kind of financial aid. And I just want to make sure that everybody knows what their options are, and that nobody is like panicked coming into the final, because a panicked mind never does as well as a calm mind. So if you want to talk about grades, if you're worried about your final grade, if you're in that kind of panic state or feeling trapped, please don't just suffer through this and cruise and take the L. Come see me and let's figure something out so that this isn't a net negative experience for anybody. I want it to be a net positive experience. I mention that now because on the day of the final, I can't do this anymore. So the last day for me to make moves like that on your behalf, I think is probably today. I'm not sure if I will be able to do it over the weekend. I know I definitely can't do it after the final. And I think that the way it works is the last day where I can do any sort of late withdrawals or incomplete moves is the last day of class, which is today. So our last opportunity to do that shit is about to go by. And so if you are feeling like you're trapped or you're about to have a net negative experience with this class, please make a point of coming to talk to me today in office hours. We will figure it out. I think that's all the announcement-y stuff. Remember the study guide. Three is written solutions to homework 11. Please don't forget to scan and submit these. They are due on the day of the final. Which again is 8/11. Okay. Any bookkeepy announcement-y type questions for me? Any stuff like that before we get into some problem solving?
I do.
Hey, what's up? Yeah.
So on the homework 11, on the last question 23, I was working with that one with the tutor, and they disagreed with the answer.
Oh, that's interesting. I love our tutors. From time to time, they get things wrong, but from time to time, you know, other things go wrong too. Which you said it was in homework 11?
Yes, I just want to understand what was happening.
Yeah, sure. Which problem was it?
23.
3. Could it maybe have been homework 10? So I've got homework 11 pulled up here, and it appears to only have 22 problems.
Homework 11. I think it was the last one. It was the one that looked like a graph.
Let me take a look here. So Zach in chat asks, how is the final going to be structured?
That one.
This way. Okay, yeah, so homework 10, number 23. Zach, the final is going to be structured the same way our earlier midterm tests have been structured. So they will be very similar to the tests you've taken already in Canvas. It's going to be an honor lock proctored thing. It'll be set up as a Canvas quiz and then a separate assignment for you to submit your written work for the free response questions. So just like exams 1 and 2. The final will be just like exams 1 and 2, only a little longer. Okay, let's take a look at this problem. And then any other problems that you guys want to look at, we can spend the rest of class just solving problems because we've covered everything we need to cover. So this is I'll write this down. So capital F is the integral from 2 to x of little f, and little f is graphed below. So this is the t-axis, and 1, 2. Yeah. All right, so you're hitting here, we're hitting here. We're starting somewhere up here. Then we go up for a minute. go down equally far. Do something like this. Okay. So they want to know which is largest. Capital F of 0, capital F of 1, capital F of 2, capital F of 3, or capital F of 4. This looks like it might be some sort of shifted sine or cosine wave. It's not easy to say for sure, but the question is, if I define some new function, capital F, as the integral from 2 to x, right? And I'm reading that right, 2 to x. Which is largest? F of 0, is F of 0 an option? Yeah, F of 0, F of 1, F of 2, F of 3, F of 4, F of 5. F of 0 through F of 4. So what we're doing there, if you drop an x somewhere in here, then capital F of x is the area from 2 to x. But remember, it's measured as negative if that area is below the x-axis and positive if the area is above the x-axis. But you also have to be careful about orientation. So if we were to integrate moving forwards like this, then this area would be measured as negative because it's below the x-axis. So f of 3, f of 4, f of 5, those are all negative. What about f of 1 or f of 0? Let me draw the picture going the other way. So again, here's like 5, 2, 4, 3, 1, 0. If I dropped an x somewhere over here, so this is f of x is the integral from 2 to x of little f of t dt, where x is assumed to be bigger than 2. And here f of x is defined the same way. Integral 2 to x, not 0 to x, 2 to x, little f of t dt, where x is assumed to be smaller than 2. Right, so at a glance, my first thought, if x is bigger than 2, then you're looking at some chunk of this area here, which is all going to be measured as negative because it's below the x-axis, or below the t-axis, sorry, it's below the horizontal axis. If you drop an x somewhere to the left of 2, then you'll be getting area which is at least above the horizontal axis, so it will be measured as positive. But also you're integrating from 2 backwards to x. So you could end up with a negative there also. So here, if x is assumed less than 2, then the integral 2 to x f of t dt could be thought of as negative integral x to 2 f of t dt. And this piece, without the negative here, this would be positive. But this is going to be making things negative. In other words, I suspect f of 2, which is 0, is the largest value. Because if x is larger than 2, capital F of x is going to be negative because you're measuring from 2 to x, you're measuring in the positive direction, going from left to right, area which is beneath the horizontal axis, so that will be counted as negative. And if you put x to the left of 2, somewhere over here, you're measuring area which is above the horizontal axis, so that would normally be counted as positive, but the integral isn't from x to 2, it's from 2 to x, so that's that flipping orientation. here, if x is assumed smaller than 2, which is necessary for us to be over here where the area is positive, then the number up here is actually smaller than the number down here. So the natural thing to do is to flip the bounds over, putting the smaller number on the bottom. And that will make the integral positive because I'm measuring area above the x-axis or above the horizontal axis with a positive orientation. But I'll get this negative out front from flipping the bounds. So I think here's my conclusion from this. For all x except for 2, capital F of x is negative. Capital F of 2 itself is 0. So among f of 0, f of 1, f of 2, f of 3, all the way out to f of 4, I think capital F of 2 is largest. So this is a very tricky problem. It requires you thinking quite carefully, not just about areas and the relative sizes, and not even just about whether the area is above or below the x-axis, but also thinking about orientation, whether you're going from left to right or from right to left. So I suspect that capital F is always negative unless x is equal to 2, in which case capital F is equal to 0, because the area from 2 to 2 is definitely 0. So we can check this by looking at the key, but yeah, my strong suspicion is that it's this guy.
So the way I thought of this one is like the delta x, because clearly, like, you know, our x is b and then our 2 is a, right? Is that something along the lines of what we're talking about?
I'm sorry, give me just 1 second. I'll be able to answer your question, Damon, in just a second here, thinking about delta x's. Hello? Oh, hey Pops, how's it going? Right around 100 pounds. Mm-hmm. Yeah, I mean, I think last time I had him weighed, he was at like 89, 90, but that was a couple of years ago. He's gotten a little bigger since. Okay, I can do that. Do you mind if I give you a call back in a little bit though? Because I'm actually in the middle of a Zoom lecture right now. Half of everything. All right, thank you so much. Bye, Pops, love you. Sorry about that. My dog is sick, so we're doing what we can. Yeah, so f of 2 is the correct answer here. And I think probably the cleanest way to think about it is that for all x's besides 2, capital F of x is negative. But you're gonna have to think very hard about why capital F is negative. Damon, when you say you're thinking about delta x's, can you be a little bit more descriptive so I can give an answer that is more certain to be correct?
Yeah, so when the x is like, you know, less than 2, the way I looked at it in the integral is, you know, the x is the b and then the 2 is the a. So like the b minus a, obviously it's going to come out negative. Like the b
You're thinking in terms of Riemann sums. Yeah. So your delta x that we use when we calculate Riemann sums, the b minus a over n, it's true that this is negative for any of these guys, right? Yeah, because x is your b and 2 is your a, if x is less than 2, then delta x would be negative. So all the terms in the Riemann sum for these guys would have a negative number being multiplied. That's true, and that's a fine way to think about why these guys are all negative. Yeah, I like that.
Can we step away from the picture so I can take a picture?
Sure. And Angelica, yeah, that would be fine. That would be fine. I think that you might want to look into registering as an audit, which should be free. If they're not able to do that for you, if they want to charge money for you, though, I can just I can add you, I think, to the Canvas class so that you would be able to get the Zoom links and all that stuff. The only catch would be unless you bought a WebAssign access code, you wouldn't be able to do the homework, which is going to make it a little bit harder to get the stuff all the way in your brain. But it would definitely be better than nothing for sure. Okay, yeah, so this is this problem. It's definitely very sneaky. We could ask the same question, but if I swap this 2 for a 0, I think that might be a good way to practice. If this problem as it's stated here is a little bit challenging, we can step back and make it a little bit easier by asking, what about, I'll call it capital G of x as the integral from 0 to x, little f of t dt, where little f is still that same function. Which of those should be largest? G of 0, G of 1, G of 2. So this was like, what was it? 4 was like right here, right? And this was 2. This is 1. So now I'm measuring, my integral starts at 0. And we can ask which one should be largest, you know, G of 0, G of 1, G of 2, G of 3, G of 4. So if I integrate from 0 to 1, that's going to give me like this area. If I integrate from 0 to 2, that's going to give me this area. And all of that would be counted as positive. If I integrate from 0 to something past 2, then I'm going to start getting bits of this area, which would be measured as negative. So which of these, G of, so who's largest? G of 0, G of 1, G of 2, G of 3, G of 4. Does anybody have a conjecture here? Certainly G of 4 represents the most area, but I don't think G of 4 is the largest number.
It'd be 2.
Yeah, exactly. Here, this is 2. If I go all the way out to 4, I'm going to get all this positive area and all this negative area. So you'll end up subtracting this away from this. If I go out to 3, I'll still have some of this negative area, which is going to subtract from this positive area. So the way to maximize the size of that integral is to get all of this positive area and none of this negative area. So G of 2 here would be the largest again, but for very different reasons, right? G of 2 is positive, strictly positive here. So I would try thinking about some problems like this where you don't start kind of in the middle. But Damon's explanation, the delta x being negative for all the Riemann sums where x is less than 2 is a valid explanation if you prefer to think of it that way. Okay, let's look at some more problems. What else would you guys like to work on? What else feels weird or hard? What else are you nervous about seeing on the final?
Substitution, for sure.
Anything,
Substitution?
Professor, honestly. Anything and everything.
Well, hopefully not everything is feeling scary, but we can look at some stuff. So I know trig stuff tends to be a little bit intimidating. What do we want to do? All right, yeah, here's one of my favorites. I put this on exam 1 for some Calc 2 kids a few years ago, and almost nobody got it. I was surprised. Zach, the optimization stuff is min-max stuff. So we did not cover the applied optimization. We stuck just to the pure mathematics. There is a section that's all word problems. which are min-max problems that have to do with the real world, and we did not have time to cover that before exam 2. So while you did learn optimization techniques, we did not talk about applying them to the physical world. It's unfortunate, but if that's something that you would like to discuss, we can definitely go over those things. Popping the e to the x off the top is a good move, yeah. So I can write this as 1 over 1 plus e to the 2x times e to the x dx. Yeah, this smells like arctan, doesn't it? Before we can actually go about calling this an arctan thing, though, remember we got to get it into the form like 1 over 1 plus x squared. And I think the trick to doing this is recognizing e to the 2x is the same as e to the x squared, like that. And then we'll make a little substitution. Okay, we'll do that next, Angelica. So what could I substitute for here to make this look like an arctan thing?
EX for U.
Yeah, we'll let u be e to the x so that du is e to the x dx, because the derivative of e to the x is e to the x. To put all my little substitution stuff in a box there. So this is du, and this piece will be 1 over 1 plus u squared. And that is definitely arctan, right? That's arctan of u. Which is the inverse tangent of e to the x plus c. Yeah, I think doing one of those graph sketching problems would be a wise thing also, where we use first and second derivative information to draw a good graph. Let me grab one from the textbook so I don't accidentally create a monster. So those were back in chapter 4, summary of curve sketching. What's a nice example? We haven't done much with like rational functions. Let's do something like that. Something a little sneaky. It's cubed. 25 looks like it would be nice and challenging. We can do this. What else looks good?
Yeah, so like square roots on the bottom.
Or maybe 19. Let's start with 19. 19 looks like it would be a little bit more tame than 25.
Can I also take a photo of the substitution one you just did?
Yeah. Here, I'll come back to this, and then we'll start on the next one.
I do have a little question on this one.
Sure, yeah, what's up?
So when we factored out e to the x, I was looking at the e to the x on the bottom, but why didn't we factor that one out as well? It's not being multiplied by 1, so it's technically itself.
Well, so because it's being added to 1, so I actually don't have a common factor of e to the x downstairs. So the 1 plus e to the 2x, I would have to have a common factor of e to the x downstairs in order to do that. And because this part right here doesn't have a factor of e to the x, I can't, there's no natural way for me to factor in e to the x from the bottom. Like I could do something like this. It's called force factoring. If I wanted to factor in e to the x out, I have to ask, okay, well, what would go in here so that when I distribute e to the x, I get this. So the 1 would become a 1 over e to the x, and e to the 2x would become an e to the x. So we could factor it like this, that denominator. But because this guy, it's not a very natural thing to do because this doesn't have a copy of e to the x. So in order to factor, whatever you're factoring has to be common to all the terms. And the denominator here has two terms, the e to the 2x and the 1. E to the 2x has two copies of e to the x. That's e to the x times e to the x. But the 1 doesn't have any copies of e to the x. So in order to factor an e to the x from that expression like this, I would have to do something a little bit perverse to that 1. I would have to, it would be what's called force factoring. Kind of like if I want to factor a 2 out from this, 1 plus 4, I could factor a 2, but that's going to be a 1/2 plus 2 here, because the 1 here didn't have a copy of 2 to give me in the first place. So if I want to factor a 2 out from this, I have to do something kind of weird here. Does that make sense?
Yes, it does. Thank you.
Cool, cool. Okay, then let's come back to that curve sketching problem. That was x cubed over 1 plus x cubed. It's number 19 from section 4.8. 4.5. So the two most important sections before we talk about any integration are probably the min-max section, which was, affect the shape of the graph, like 4.1 and 4.3, and then 4.5. So those are probably the sections that contain the most crucial skills for you going forwards when you talk about application problems like you'll see in physics or chemistry. And then for Calc 2, the chapter 5 stuff is certainly the most important because that's where you will be picking up in Calc 2. So this is a really good example of a problem. First, we should find the domain. And here, this is going to be all real numbers except whatever makes the bottom 0. So we set 1 plus x cubed equal to 0. There's more than one way to solve this. You can actually factor 1 plus x cubed as a sum of squares. That's 1 plus x times 1 plus x squared, same, or no, 1 minus x. Yeah, same, opposite, always positive. So this is using the sum of squares, or sum of cubes formula that says a cubed plus or minus b cubed can always be factored as a plus minus b times a squared minus plus ab plus b squared. So the sum of cubes formula is a nice trick. You could also subtract the 1 and take cube roots. In any case, this has no real solutions, no real roots. So the only solution is -1, makes the bottom 0. So your domain here is -infinity to -1, unioned with -1 to infinity, or all real numbers except for -1. We would like to look for any symmetries or periodicity, asymptotes, and intercepts before we dig into the calculus stuff. Check for symmetry. This might be an odd function, but it's not. It's definitely not even. So that would be -x cubed over 1 plus -x cubed. And upstairs, the negative of x all cubed is the negative of x cubed. Downstairs, we'll get 1 minus x cubed, though, not 1 plus x cubed. So this is not equal to f of x, nor is it negative f of x. So there's no symmetry. F is neither even nor odd. Intercepts. The y-intercept is always the point 0, comma f of 0, which here is, if you plug in 0 for x, you get 0 over 1 for f of 0, so that's 0, comma 0. And x-intercepts, we would set the top to 0. So remember, y-intercepts, you always just plug in 0. Here you set the top equal to 0. But x cubed is equal to 0 only at one place, and that's at 0. So in other words, your x and y-intercept are the same point. There's only one x-intercept, and it is the same point as the y-intercept. So nothing too interesting or exciting when it comes to intercepts. Asymptotes. I do have a vertical asymptote where the bottom is 0. That's -1. And horizontal asymptotes, I need to consider the limit as x goes to infinity of f of x, which is the limit as x goes to infinity of x cubed over 1 plus x cubed. And if you divide top and bottom by x cubed, you see that this is the same as 1 over x cubed plus 1. And in the limit, that's 1 over 0 plus 1. So y equals 1 is an HA. And the limit as x goes to negative infinity works the exact same way. Right, we would do all the same steps. We would divide top and bottom by x cubed, and then this piece right here would go to 0. So on both sides, the function approaches the line y equals 1, and we have a vertical asymptote, x equals -1. So I think these are all the little things we would want to do before we start any of the calculus. Now I'll take the first and second derivative. F primed of x is d dx of x cubed over 1 plus x cubed. And for this, we would want to use the quotient rule. So that's low d high minus high d low over low low. So my denominator here is 1 plus x cubed all squared. And upstairs I'll have the bottom times the derivative of the top. So that's 1 plus x cubed times the derivative of x cubed is 3x squared. Minus the top, which is x cubed times the derivative of the bottom. The derivative of the bottom, though, the 1 would differentiate to 0, and x cubed differentiates to 3x squared. So that's coming from the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the square of the bottom. I can distribute and combine like terms. So here I'll have 3x squared plus 3x to the 5 because x squared times x cubed is x to the 5 minus 3x to the 5. And all of this is over 1 plus x cubed quantity squared. So f primed, the 3x to the 5's cancel, and we get 3x squared over 1 plus x cubed all squared. That's f primed. So I can make my number line for f prime.
So this is where I get tore up, is how many number lines and what do I put on each number line? I think I get lost in my work.
So the f prime number line is going to tell us where the function is increasing and decreasing, which is also going to tell us the location of any mins or maxes. The f double prime number line is going to tell us where f is concave up or concave down. Sometimes I also like to make a number line for f itself to figure out where f is positive and where f is negative. So if you have the time, I would do all three. But the bare minimum is the f prime and f double prime. So you need at least two. F prime to tell you where you're increasing and decreasing, f double prime to tell you where you're concave up or concave down. And then sometimes if you have extra time and you're nervous about your graph not coming out beautiful, you can make a number line for f itself. Here it's fairly clear that f itself will be positive if x is positive and negative if x is negative. But there may be a subtlety coming from the vertical asymptote, so we'll do all three here. But let's do f prime first. So f primed is equal to 0 if x is 0. So I can put 0 here. It's also undefined if x is -1. So I'll put -1 on my number line. And then I don't think there's any other critical numbers for f. So f prime equals 0 when x equals 0 and is undefined when x equals -1. So those are the two numbers that go on his number line. If I test something over here to the right of 0, like 1, the numerator will be 3, and the denominator would be 1 plus 1 squared, which is 4. 3/4, which is positive. So here we are positive. As I jump over the 0, that 0 is coming from this even multiplicity factor in the numerator. So f prime will not change sign. You could also test like -1/2. If you plug -1/2 in here, the numerator would be positive 3/4, and the denominator, -1/2 cubed, is -1/8. Then you're going to add 1 to that, but then you're going to square it, so that's going to be positive also. So we're positive in this region. And if we test something to the left of -1, like -2, then the numerator here, let's see, -2 squared, that's positive, right? So that would be a positive 4, so the numerator would be a positive 12. And downstairs here, what would we have? You'd have -2 cubed, which is -8, plus 1, which is -7. Oh, but then we're going to square that also. In fact, you see the top and bottom are both being squared. So you know that f primed is always positive. So we're increasing here, we're increasing here, and we're increasing here. Now at -1 and at 0, at those points themselves, we're probably not increasing. In fact, the function we know is undefined at -1. We have a vertical asymptote there. At 0, we might have something kind of interesting going on. It's not a min or a max, but it could be something like we have this brief horizontal tangent line, and we're increasing to the left and the right of it. So something like this going on at 0. To sort out concavity, we'll need f double primed. So you get to practice differentiating with the quotient rule a little bit more. That's d dx of f primed, which was 3x squared over 1 plus x cubed squared. So we'll take the bottom times the derivative of the top. That's 1 plus x cubed all squared times the derivative of the top is 6x minus the top times the derivative of the bottom. And the derivative of the bottom requires the chain rule. So that's going to be 2 times 1 plus x cubed to the 1. That's the derivative of the outer, leaving the inner alone. And then I multiply by the derivative of the inner, which is 3x squared. And all of this goes over 1 plus x cubed squared, which is 1 plus x cubed to the 4. So the derivative of the top here is 6x. The derivative of the bottom here is 2 times 1 plus x cubed to the 1 times 3x squared, which required the chain rule. So we've got low d high minus high d low. That's our quotient rule here. And it's getting a little bit gnarly, but still quite manageable. I'm gonna have to FOIL this out and then distribute this. I'll distribute everything here and combine all my like terms and hope that I get something nice. So foiling here, I get 1 plus 2x cubed plus x cubed times x cubed is x to the 6. And all of that has this 6x attached to it. And then minus, so this is one chunk here because everything in there is being multiplied. Let's put the 3x squareds together. That's 9x to the 4. And then I've got my 2, so let's call that 18x to the 4. And then I've got my 1 plus x cubed. And all of this is being divided by 1 plus x cubed to the 4th power. And now we can distribute. So this will be 6x plus 12x to the 4 plus 6x to the 7. That's from this distributing this first guy. 6x times 1 is 6x. 6x times 2x cubed is 12. 6 times 2, x to the 4, x cubed times x. And then 6x times x to the 6, that's 6x to the 7. And over here we'll have minus 18x to the 4, distributing to the 1, minus 18x to the 4. So x to the 4 times x to the 3, that's x to the 7. And all of this is over 1 plus x cubed to the 4th power. So f double prime, let's see what we get. I've got minus 18x to the 7 and plus 6x to the 7. So that's minus 12x to the 7. What about x to the 4s? I've got here a minus 18x to the 4 and a plus 12x to the 4. So that's going to be minus 6x to the 4. So that's the x to the 7's done. The x to the 4's done. They don't cancel. I've just combined them and I'm coming back here to see what's left. Plus 6x. All right. And this is all over 1 plus x cubed to the 4th power. So I can factor an x from the numerator and try to see what else can be done from there. Let's factor a negative 6x from the numerator. So then this would become a positive 2x to the 6. This will become a positive x cubed. And this would become a minus 1. So this derivative is pretty gnarly.
I have a question.
Yeah.
When you first derived 3x squared at the top, at the end of the high d low, low d high, where did that come from?
This guy?
Mm-hmm.
This guy came from the chain rule, from the derivative of the bottom.
Oh, shoot. I always forget that bit. Okay, thank you.
Yeah, the chain rule is kind of sneaky like that. So it can be helpful to come off to the side and calculate the derivatives of the top and the bottom as a separate thing on their own, just to make sure you don't miss little stuff like that. That's probably a good idea. Any ideas what the hell I can do with this? I definitely need to factor this, but it's a 6th degree polynomial. So what could I do to try and factor this?
We can't pull out x cubed because you have the -1.
Yeah, unfortunately, there's no more common factors. I pulled out the largest common factor.
But I set that to 0 and then pull out an x3 so I can work with it.
That would have the same problem as what Angelica was saying. Again, I don't have a common factor. And factoring is only useful if the whole thing is equal to 0. If I set this equal to 0, and then I wanted to pull out an x cubed, I would have to get rid of the 1 somehow, which would mean I'd have like this.
Not if I were to add 1 to both sides, then factor out an x cubed and then work from there.
It's true that you could do that. That's algebraically sound, but unfortunately it's not helpful because the whole business of factoring, I can't say if I have 2 factors equal to 1, then one of the factors must be 1, the same way I can with 0. So something like this.
What about 2x?
Something like this is true, but it's not useful because if I factor on the left, then I still can't do that thing where I would set each factor to 0 because the right-hand side isn't 0. So this is okay, but not useful. We can factor this thinking of it as a substitution. So we won't do this. But what we can do is think of this as 2 times x cubed squared plus x cubed minus 1. Some people like to write this with a little like u equals x cubed and then say this is 2u squared plus u minus 1. We also do this in trig classes, right? Where you substitute for like sine theta and then you factor in terms of the new variable u. So I can factor this guy using the AC method. I've got a 2 times -1, so I need 2 numbers that add up to +1 and multiply to -2. That's going to be +2 and -1, so this is 2u squared plus 2u minus 1, which is 2u times u plus 1 minus 1 times u plus 1. So we get 2u minus 1 times u plus 1, which is 2x cubed minus 1 times x cubed plus 1. So f double prime can be factored as, let's give ourselves some space to work here. So f double primed is -6x times 2x cubed minus 1 times x cubed plus 1 all over 1 plus x cubed to the 4. And this factoring trick is something that might be lost deep in the annals of pre-calculus. It's understandable if you don't remember this right away. But the giveaway here is that x to the 6th is x cubed squared. So I can do this little substitution and treat it like a quadratic, and then plug back in for x cubed. So now I see that f double prime will be 0. Let's see, I've got a factor of x cubed plus 1 here. I can cancel that. I get -6x times 2x cubed plus 1 over, this factor cancels with one of these, so I get 1 plus x cubed all cubed. So now I set the top and bottom equal to 0, so f prime prime equals 0 when, let's see, -6x equals 0, that means x is 0. Or when 2x cubed plus 1 equals 0, that's the same as saying x cubed equals -1/2, or x is the cube root. So negative can pop out, cube root of 1/2, like this. So these are the numbers that I'm going to put on my number line for f double primed. It's also undefined when the bottom is equal to 0, that's when x is equal to -1. So all of my f double prime stuff is there. F prime prime. So definitely -1, 0. Oh wait, this is also negative. And the cube root of -1/2, let's see. So I think that should be, yeah, that is still to the right of -1. And then 0. And we can grab some test points. If we grab something to the right of 0 over here, like 1, then this piece will be -6, this piece would be 3, and this piece would be 8. So we get -18 over 8, which is definitely negative. As I jump over the 0 came from this multiplicity 1 factor, so I will change sign. As I jump over him, this will be a plus then. Unfortunately, these guys I don't have factored all the way down. I can't say what the multiplicity is that this guy came from, not immediately. If we factored this as a sum of cubes, you would find that there's a multiplicity 1 factor hiding in there. But it would be safer to grab a test point. So let me get a decimal approximation. The cube, oh, no, not that. I need the scientific calculator. The cube root of -1/2 raised to the 1/3 power. It's like -0.79. So between, I'll copy this here. So this number, the negative cube root of 1/2, the cube root of -1/2, that's like -0.79. So we could test something in here, like -0.8. It's going to be a pain in the ass. Let's do it. It's all right. So try to have this in a place where we can see everything. -6 times -0.8. times 2 times -0.8 cubed plus 1, all divided by 1 plus -0.8 cubed. Now we see that it's negative. Oh, this needs to be cubed also, right? Yeah. Still negative though. So this piece here, we're negative. And in here we tested x equals -0.8. Because I know -0.8 is between -1 and -0.79. And then to the left of -1, we could test like -2. So when you plug in x equals -2, this will be positive. This piece right here, -2 cubed is -8 times +2 is -16 plus 1 is negative. So the top, this piece would be positive, this piece would be negative, so the top is negative. And if I plug a -2 down here, this would be -2 cubed is -8, plus 1 is -7. -7 cubed is definitely negative, so the top and bottom are both negative. So over here, f double prime will be positive. So this is my number line for f double prime. I never made the number line for f itself, so let me go ahead and do that, and then we'll put all this together. Your book doesn't talk about doing this for f itself, but when we teach how to graph these things in pre-calculus, the number line for f is all we have, and I feel like it's silly to throw that out. F of x is x cubed over 1 plus x cubed. So we know -1 is on there, and we know 0 is on there. because the top is 0 when x is 0, and the bottom is 0 when x is -1. If I test something to the right of 0, like +1, I get 1 cubed over 2, which is definitely positive. Hopping over the odd multiplicity factor, we will change sign. And then if we test something to the left of -1, like -2, the top here would be -8, the bottom here would be -7. That ratio is negative over negative, so that will be positive. So then we can summarize everything. Get my f prime number line back where we can see it. Zoom out a little. Yeah, okay. So here you see the f prime line, the f double prime line, and the f line. Let's try to summarize. So I've got -1, 0, and the negative cubed root of 1/2. That's what's going to go on my summary. Okay. To the left of -1, f is positive, increasing, and concave up. Because all three, f, f primed, and f double primed, are positive. Between -1 and the negative cube root of 1/2, f primed is positive, f double primed is negative, and because we are now to the right of -1, f itself is negative. So here we are negative, increasing, and concave down.
Oh shoot, so we don't do like we did in pre-calc and do a negative, a positive, a negative is gonna be positive. We just write it all down.
Yeah, that's how I prefer to do it, yeah.
I'm so silly.
Oh, you're all good. So then what about between this negative cube root of 1/2 and 0? F primed is definitely still positive. What about f itself? Well, we're still between -1 and 0, so f itself is negative. We're increasing because f primed is positive, and f double primed switches back to being positive here, so we're concave up. And then to the right of 0, f itself is positive. F primed is positive, so we're increasing. And f double primed flips back to negative, so we're going back to concave down. So here is my summary from all that work.
So in the area where we have our negative 0.79, that's not included in f prime and f.
Yeah, he wasn't a special number for f primed or for f, right? He didn't make f 0 or undefined, and he didn't make f primed 0 or undefined. That number was only important for f double prime. But on my summary number line, I always put all the information from all of the number lines.
Because it has a concavity there.
Right.
Oh geez. I think that's what throws me. I'm like, what do I do with this?
So sometimes it can be useful to remind yourself where each of these comes from. You can see the sign changes. F is negative, f primed is positive, but f double primed flipped to negative. Over here, f was negative, f primed was positive, and f double primed flipped again. So what we have here are a lot of inflection points, a lot of places where concavity changes. And here f is positive, F primed is positive, and F prime primed is negative again. So everywhere F prime prime flips from positive to negative, our concavity changes. We go from being concave up to concave down or vice versa. F primed is always positive, so I don't have any mins or maxes. I never go from being increasing to decreasing. I'm always either increasing or having a brief horizontal tangent. And F itself changes sign twice. F is positive to the left of -1, negative between -1 and 0, and then positive to the right of 0. So if I want to put all this stuff into a graph, I would start by drawing in my asymptotes and intercepts. Unfortunately, there wasn't a whole lot of information there. If this is 1, then I know I have a horizontal asymptote y equals 1. Yeah, these problems do go on for quite a while, especially as the derivatives get more and more complicated. I know I've got a vertical asymptote over here at -1, x equals -1. So this is my HA, y equals 1. I've got a VA here. X equals -1. I know I go through the origin here. And since F is positive all the way out to the left, well, I guess I can't really say that for sure yet. So let's not do that. So what can I say? What can I start drawing in? I know that F everywhere to the right of 0 is positive, and I know I go through the origin. So because I'm coming up from down here, I cross like this, right? To the left of 0, F is negative. To the right of 0, F is positive. So this has to be some sort of cross here. Also, we go from being concave up to concave down. So over here, I'm increasing concave down. Over here, I'm increasing concave up. So I've got something, let's see, is F prime, was F prime equal to 0 there? Double check. Yeah, F prime was 0 at 0, right? So this was one of these things that we detected. We've got a shape change like this. It actually turns out to be going from concave down, or so from concave up to concave down. So here I have an HTL, and I went from concave up and to concave down. So it's something like increasing concave down. That looks like this. And then increasing concave up, that looks like this. So something like that, some kind of wonky behavior there. I know I'm going to be approaching this guy like this. I know I'm increasing concave down here, brief horizontal tangent, increasing concave down. So increasing concave down looks like that. Increasing concave up over here. It's like this, but I should also have a horizontal tangent in here, which isn't quite making sense. Negative, positive, so each cross. Increasing, increasing, so we're like this. Concave up, concave down. So concave up, something like this here. And then at the negative cube root of 1/2, I'll just call that negative 0.79. I know I had an inflection point where we went from being increasing concave down to increasing concave up. I've already got my increasing concave up bit here. So we're increasing the whole time, but our concavity changes. So we're like this. Oh yeah, sure, sorry.
That's okay.
So I've got my IP here. I've got an IP here. And then that means I'm going to have to approach this HA like that, or the VA there like that. And then what other information do I have? I know that to the left of -1 over here, F itself is positive, so I've got to be coming along this VA like this. I know that over here I'm increasing and concave up. Over here, I'm increasing concave down. And did I have any other interesting stuff here? No, just like that. So concave up, concave down, that's from the VA. Concave down to concave up, that's this IP. And then concave up to concave down here. Okay, so yeah, there's nothing else crazy going on over here. So this guy's something like this. And then this piece has to connect over to this guy. So something like this. So you see we're everywhere increasing, right? As you go left to right, we're always going uphill, always going uphill. And then I've got these two inflection points here. One at this guy, where we go from being concave down to concave up. And then one here at 0, where I go from being concave up back to concave down. Now my one concern is that at 0, I should also have a horizontal tangent, because f prime was equal to 0 at 0. So I should have this very brief horizontal tangent, something like that. But if I'm going to be increasing concave down to increasing concave up, I could do it like that. But I don't think I could be increasing concave up to increasing concave down and do something like that. So increasing concave up looks like this, and increasing concave down looks like this. And the only way I could connect those is not with a horizontal tangent. So I think there might be something weird going on here at 0. But this is a pretty good graph. So let's take a look and see what Desmos says. What's going on, Desmos? Nothing calculator. This was x cubed over 1 plus x cubed. Okay. Yeah, no, it's pretty good. It's pretty damn good. It looks like the IP that I put over here should actually be over here. And this is what's going to give us the ability to get the concavity right. So let me come back to my f double prime calculation and see what I did wrong there. Should that be a positive cube root of 1/2? So f double primed. Ah, yeah, here it is. This is 2x cubed minus 1. And when I factored the -6, or no, it wasn't that. When I canceled the x cubed plus 1, I accidentally changed that to a plus. So this should be a plus, which means this guy should be a plus. So we can go rework our f double prime line. It's hard not to make a little mistake anywhere. It really is. So f double primed, he gets interested at -1, 0, and the positive cube root of 1/2, not the negative cube root of 1/2. And
-6x times 2x cubed.
2x cubed minus 1.
Oh, okay, I wrote it.
I wrote it in this line before. I made a mistake where I changed 2x cubed minus 1 to 2x cubed plus 1, like a transcription error. And
Yeah.
that gave me this guy as negative when he should have been positive, because that plus is a minus, so this is a plus, and that cube root is positive. If we want to go back through this quickly without messing around with test points, what can we do? I can use my multiplicity trick. I can say that to the right over here, that numerator, this guy is definitely positive, this is negative, this is positive. So we're going to be negative over here. This is an odd multiplicity, odd multiplicity, odd multiplicity. So my f double prime line looks like that. So my summary line has -1, 0. What else do we have? -1, 0, and
-0.79.
is that it?
-0.79.
And that -0.79, that's going to be positive now, because that was the guy that I made that mistake on. So it's positive 0.79. Did we just have those 3 regions? It was 4th, -1. Oh no, just those 3 numbers creating 4 regions. Okay.
Oh, so we just swap that to go in front of the 0 because it's positive now on the line.
Exactly. Yep. Yeah, so that was my goof. So then to the left of -1, f prime was negative. F itself is positive, so we're positive, increasing. And then my f double prime tells me we're concave up. Between -1 and 0, f itself was negative, increasing. And here we switch to being concave down. Between 0 and 0.79, f itself is positive. F primed is positive everywhere, we're always increasing. And f double primed switched to being concave positive, so we're concave up. And then to the right of this guy, f was positive, increasing, and now we're concave down. So here's my correct summary. And it was in the previous working of this, I had this as negative and it should have been positive, that's all. So then from there, I can get a very nice graph. Do this a little bit more quickly. Here's my HA, y equals 1. I've got my VA, x equals -1. I know I go through the origin. I know over here, f is positive, increasing, and concave up. So that looks like this. I know that f changes to being negative here. So that means I have to come up from down here. I know that at 0, I've got that brief horizontal tangent. And then to the left of 0, I'm concave down and increasing. So this is concave down. To the right of 0, I'm concave up, increasing. So my local behavior there is like that. And then at the cube root of 1/2, I have this IP, where I change from being concave up to concave down. So it's like this. And then we come out here and approach our horizontal asymptote. And here we come down to our vertical asymptote. So yeah, this is a better graph of F. We've got our IPs. We don't have any mins or maxes, but we've got our intercepts and asymptotes all worked out. It definitely is a tricky problem. And you've seen both times during class time, I've gone through one of these longer curve sketching problems. I make a little mistake somewhere, but I could tell that I made a mistake, and it's worthwhile to get to a place where you can catch those errors. The issue here, remember, was I discussed it right here. So we knew that we had a change in concavity from our f double primed line, but I knew that I'm supposed to be increasing. So I need to go from increasing concave up to increasing concave down. And there's no way to do that if I have a horizontal tangent at that point. I can go from increasing concave down to increasing concave up, though. And so that told me that I'd made a mistake somewhere in my concavity calculations. And that's how we knew to go back and rework f double primed. So I'll concede this is definitely not simple stuff. It's not. This guy was incorrect. We had to swap him over here to be positive because I changed a minus to a plus earlier. But just like on the test, you know, if I, on exam 2, if I give you something like this, I will give you something reasonable, something that can be done much more quickly, where the derivatives are not so sloppy. Okay, how are we doing? Ooh, we're actually a little bit over time. All right. So that's it, ladies and gentlemen. That is Calc 1. You made it through. Make sure you're practicing the integration. If you want to talk about some more problems, come see me in my office hour this afternoon. I'll be there from 1 to 2. And I can try to work in like a review for the final or something like that over the weekend. I will make an announcement on Canvas letting you know when that will be. A little bit later today, I'm going to post your exam 3. It's going to be that PDF. Remember, you need to print that and fill it out and then scan it all and submit it in on the day of the final, which is next Tuesday. And then the final, remember, is not our normal time and it's not our normal day. So it's Tuesday at 8 a.m. So make sure you put that in your phone. I would go ahead and set an alarm right now. Anything you guys wanted to ask about before we get switching?
Yeah, just wanted to say thank you, Professor, for everything, for teaching us Cal 1.
That's sweet. Thank you, sir.
No, yeah, for sure. And one last thing would be, yeah, if you can make that review for the final, that would be amazing. That would honestly be like the best thing ever. So if you can do that for us, that would be great. And
The best I can probably do there is find an hour or or two on probably Sunday when we can
yeah, that's fine.
solve problems. But I'll definitely try to do that, and I'll make an announcement about it.
Cool, awesome. And this is kind of off the subject. I should email you about this, but I'll just say now. I'm taking your class, Cal 2,
Okay.
in the fall right now.
Cool.
Wait, is that strictly online, or are we going to see each other in person maybe?
Right now, it looks like it's going to be the same as this. So they call these
Okay.
hybrid classes, and I'll be running the Calc 2 the same way that I'm running this class, at least until I'm told otherwise. So for right now, everything I've heard from the college is that the math classes are all going to be online next semester in this, either the full online format or the hybrid format. I prefer the hybrid format. So it'll probably be just like this.
Cool, awesome. Thank you.
All right. Anything else, guys, before we get out of here?
Yeah, for study guide 3, are we scanning that work as well?
Say that again?
For study guide 3, are we scanning that work as well?
Yes, sir. Yeah, so the study guides, just write out the solutions to the homework 11 problems and scan those, submit them in Canvas. Yep.
When are you going to have the test 2, you know, like written stuff submitted so you can review
I'm
it?
still working on that. Yeah, I know that sucks. I just haven't had time lately. If you want to talk about particular problems from test 2, you want to see a solution, I would say the fastest way to get that is going to be to come by my office hour this afternoon. Unfortunately, my dog is very sick, so right now I've got all of my free time is kind of going into trying to take care of him. But I will do my best to get those scanned in there today.
Okay, thank you.
Professor, did you upload the solutions for test 1?
No, I don't think I uploaded a key or anything like that.
Yeah, 'cause you solved them in class, but you weren't recording, so we couldn't like go back and look at it.
I see. All right, maybe the easiest thing for me to do here so that everybody gets what they need out of that stuff is to write out a key for test 1 and 2. And that way we're not so starving for feedback from the exams. I think I can probably manage that.
Okay.
Okay, anything else before we get out of here, guys? Alrighty then, it's been a pleasure having everyone in class. Come by my office hour if you want to solve some more problems today. Remember to get exam 3 and study guide 3 turned in by Tuesday, and remember that Tuesday at 8 a.m. you have your finals. So make sure you set an alarm, make sure you got whatever you're going to need to wake up at 8 a.m. ready to go. That is it. You guys have made it through Calc 1. I will talk to you in the future, I hope.